So our next presenter is Haocong Luo. Haocong, are you there?
Yes. Can
Okay.
you hear me?
Yes, we can hear you.
Is there any like background noise or other like anomalies in my voice?
No, it feels okay at this
Okay.
point, for me at
Okay.
least.
Okay, yeah.
Yeah.
I will share my screen.
Yeah, you can share your screen. So Haocong is actually a student who is taking this class at the moment with everybody else. Actually, I mentioned this work that he's going to present in the low latency memory lecture. He's going to present capacity-latency reconfigurable DRAM. And since I already gave the basic ideas, he's going to spend a little bit less time on it, but he's going to go into more detail on how it works, why it works, and some evaluations as well. But basically, he did this work while he was doing an internship with me and my group last year, and then he recently started out as a master's student at ETH, so that he can do even more research going into the future. Okay, Haocong, it's yours.
Okay. Can you see my screen now?
Yes, it's good.
Okay. Okay. Cool. I will start. Okay. Thanks, Professor Mutler, for the introduction. I will be presenting CLR-DRAM, a low-cost DRAM architecture that enables a dynamic capacity latency trade-off. This talk is also extended and modified version of my conference talk at ISCA 2020. So this work is motivated by the fact that workloads and systems have varying memory capacity and latency demands. However, commodity DRAM as the prevalent technology for main memory makes a static capacity latency trade-off at design time. As a result, existing DRAM could not adapt to changes in the workloads and systems memory capacity and latency demands. Therefore, our goal is to enable a dynamic capacity latency trade-off in DRAM at a fine granularity, that is, a single DRAM row to meet the changing capacity and latency demands of the workloads. To this end, we propose CLR-DRAM, which stands for Capacity-Latency Reconfigurable DRAM. CLR-DRAM is capable of dynamically reconfiguring a single DRAM row to operate in either a max capacity mode with high storage density or a high performance mode that can operate with low access latency and low DRAM refresh overhead. The key mechanism of CLR-DRAM consists of two techniques. First, we can couple two adjacent DRAM cells in a row and their two sense amplifiers to operate as a high-performance single logical cell. Second, such coupling can be dynamically turned on and off to switch between the two modes. Our evaluation shows that a high-performance mode row in CLR-DRAM significantly reduces four major DRAM cell access timing parameters, as well as improves average performance and saves DRAM energy. Okay, now I will go into the motivation in more details. We all know that the long access latency of DRAM is a performance bottleneck. However, it is not intrinsic to the DRAM technology itself. There is a fundamental trade-off between storage capacity and access latency in DRAM. And commodity DRAM overwhelmingly favors storage capacity at the expense of access latency. The figure on the right, which is taken from tiered latency DRAM, illustrates how access latency and storage capacity affect each other in the conventional architecture. If we look at the sub-figure B, which shows the cost optimized or it's essentially storage capacity optimized architecture, it achieves high storage capacity by making a large number of DRAM cells sharing the same expensive peripheral circuitry, for example, the sense amplifiers. As a result, this creates long data passes like the bit lines, which contributes a lot to the long access latency. On the other hand, if we want to reduce access latency, we need to have less cells share this the expensive peripheral circuitry like the sense amplifier. This means that we have to put more area consuming peripheral circuitry, which in turn reduces the area that we can place the DRAM cells. So the motivation is that modern workloads having different main memory capacity and latency demands. Existing systems miss the opportunities to improve performance by adapting to the changes in the capacity and latency demands. The memory capacity of a system is usually over-provisioned, while many modern workloads tend to underutilize the system's memory capacity. Here, I will show some figures taken from these references. So this figure 2 is taken shows the memory utilization over a period of time of HPC workloads. As you can see, for most of the nodes, the 80th percentile and 90th percentile time memory usage is even like something below 50%. But at the same time, they will like sometimes utilize a lot of memory that is close to 100%. This shows that like for HPC workloads, the memory capacity demand is first always changing. Second, and for most of the time, it's underutilized. These two figures shows the memory utilization for cloud workloads. The sub-figure on the left shows the average memory utilization of batch workloads. As you can see, like most of the batch workloads, they don't even use more than 5% of the system's memory capacity. The sub-figure on the right shows the average memory utilization for online services running in cloud environments. Although the average memory utilization of online services is much higher than that of batch workloads, but still, like most of the jobs, they does not use more than 60% of the system's memory capacity. So these results all show that the memory capacity and latency demands of existing systems and workloads, they vary a lot, and existing systems miss the opportunities to improve performance by adapting to these changes. So commodity DRAMs, they make static capacity latency trade-off at design time, which limits their capability to adapt to these changes. And even some of the state-of-the-art heterogeneous DRAM architectures like tiered latency DRAM or CHARM, they only employ a fixed size and very small low latency region, which does not always provide the best possible operating point within the DRAM capacity latency trade-off spectrum for all the workloads. So if we take tiered latency DRAM as an example, let's assume that the near segment is of the capacity of 32 rows, as shown is the best configuration in the tiered DRAM paper. Then the fast memory region only takes up about like 6.25% of the entire DRAM capacity if the subarray size is of like 512 rows. So this capacity is obviously too small for those workloads to take advantage of. Therefore, our goal is to design a low-cost DRAM architecture that can be dynamically configured to have either high capacity or low latency at a fine granularity, like a single DRAM row, as shown pictorially in this figure. Next, I will briefly introduce how DRAM works, as well as some extended information on the common DRAM subarray architecture in the field. A typical density optimized subarray architecture is shown on the right. Unlike the simplified version introduced in previous lectures, because of the large size of the sense amplifier, the sense amplifier that is connected to adjacent DRAM cells must be placed in an interleaved manner on the top and the bottom of the subarray. And this is one of the commonly used open bitline architecture that is optimized for density. So yeah, and the sense amplifier, it actually operates in a differential manner. It reads data stored in the cell by sensing and amplifying the voltage difference across a pair of bit lines caused by the sharing of charge between DRAM cells and a bit line when a row is activated. As the animation shows, during an activation, another bit line in a neighboring subarray is also involved to serve as the reference of the sense amplifier. Here we show the brief procedure of accessing a fully charged DRAM cell. The x-axis represents time and the y-axis is the voltage level in the bit lines and the cells. So when we want to activate a row, the activation command first let the DRAM cell to share its charge with a bit line. This creates a voltage difference across the bitline pair, and when such difference is large enough, the sense amplifier will start to amplify this voltage and start the charge sharing process. And we call this this voltage difference delta VTH, which stands for the threshold voltage for the charge restoration process to start. And during the charge restoration process, when the voltage difference across the bitline pair reaches another level, we can say that, okay, the value is now like reliably latched in the sense amplifier, and we can issue read or write commands to access the data. And excuse me. Okay, and this voltage difference we denoted it as delta V RCD, and the rest of the charge restoration process just restores the charge level back to the cell, so that the value stored in the cell does not get destroyed. And when the charge at the cell is fully restored, we can issue pre-charge commands to close the row. Okay, so for clear DRAM, the key idea of clear DRAM is to enable dynamic configurability of the connections between DRAM cells and sense amplifiers. In the density in the density optimized open bitline architecture, which is shown on the left. To do so, clear DRAM, which is shown on the right, adds two types of small isolation transistors called type 1 and type 2 bitline mode select transistors to enhance the connectivity between DRAM cells and sense amplifiers. For a row to operate in max capacity mode, clear DRAM enables type 1 isolation transistors and disables type 2 isolation transistors to mimic exactly the same cell to sense amplifier connections as in the open bitline architecture. Doing so enables every single DRAM cell and its sense amplifier to operate individually, thus achieving the same storage capacity as a row in the conventional density optimized open bitline architecture. For a row to operate in high performance mode, clear DRAM enables both types of isolation transistors to enable two kinds of coupled operations simultaneously. First, two adjacent DRAM cells in a row are coupled as a single logical cell because they're both connected to both ports of the same sense amplifier. Let's say these two cells, they are all connected to sense amplifier 1 at the top. Second, two sense amplifiers which originally served the two adjacent DRAM cells individually, are now coupled to operate as a single logical sense amplifier because this logical cell is connected to both of the two sense amplifiers. So as we can see in this figure, both the sense amplifier at the top and the bottom, they both connected to the logical cell formed by these two adjacent DRAM cells, and they are connected with the same pair of bit line. So they essentially operate as a single sense amplifier. A high performance mode role has reduced access latency and DRAM refresh overhead via these coupled cell and sense amplifier operations, which I will explain in later slides. Now I will give a brief overview of how these coupled operations in high performance roles reduce access latency and refresh overhead. I will start by describing what these two couplings enables respectively. First, a logical cell always stores opposite charge levels in the two coupled cells to represent the same bit of data. This is because the sense amplifier always drives the two bit lines that each of the coupled cells is connected to into complementary voltage levels. This property of a logical cell enables three benefits. First, it reduces the latency of charge sharing. Second, it enables the early termination of the charge restoration process. Third, it enables retaining the data stored in the logical cell for a longer period of time. A logical sense amplifier operates faster by having two sense amplifiers driving the same logical cell from both ends of the bit lines. This also has three benefits: the reduction in the latency of charge restoration, the reduction in the latency of pre-charge, and enables the DRAM refresh process to be completed in a shorter period of time. Now, I will go into more details on explaining how these coupled operations reduces DRAM access latency. As a recap, the coupled operations of two cells and two sense amplifiers reduces DRAM latency in three ways. The reduction of charge sharing latency, the early termination of charge restoration, and the reduction of the latency of the entire charge restoration process and pre-charge. As a result, a high performance mode in clear DRAM reduces TRCD, TRES, and TRP. The opposite charge levels stored in the logical cell reduces the charge sharing latency by driving both bit lines of the same sense amplifier into opposite directions during charge sharing. It reduces charge sharing latency because the voltage difference across the bit line, across the two bit lines, reaches the threshold voltage required by the differential operation of the sense amplifier earlier than the baseline case where only one DRAM cell is involved during charge sharing. The opposite charge levels stored in the logical cell also enables a high performance mode role in clear DRAM to terminate its charge restoration process early. We make two observations about charge restoration process. First, the charge restoration process has a long, let's say, tail latency. Our motivational SPI simulation shows that it takes about half of the charge restoration latency to fully restore the last 25% of charge in a charge cell. This means that if we terminate the charge restoration process earlier, the charge level restored in the cell does not degrade significantly. Second, a discharge cell restores much faster than a charged one. This is because the restoration current of a charging cell is limited more than that of a discharging cell. In other words, if we terminate the charge restoration process of a logical cell earlier, we can still have the discharge cell fully restored. Leveraging these observations, we reduce TRES by terminating the charge restoration process early. Our SPICE simulation shows that TRES could be significantly reduced with only a marginal negative impact on the reduced TRCD due to the reduced charge level in the cell prior to deactivation. The logical sense amplifiers reduces the charge restoration latency simply by having two physical sense amplifiers driving the same logical cell from both ends of the bit lines. This enables faster charge restoration, thus largely offsets the long latency introduced by long bit lines in the density optimized open bit line architecture. The pre-charge latency is also reduced because two pre-charge units which are associated with the sense amplifier are also coupled to pre-charge to equalize the bit lines together during the pre-charge process. As a result, by having the coupled operations of two DRAM cells as a single logical cell and two coupled sense amplifiers as a single logical sense amplifier, CLR-DRAM reduces these three major DRAM cell access timing parameters. Now let me explain how CLR-DRAM mitigates DRAM refresh overhead in high performance mode. CLR-DRAM reduces refresh overhead of high performance mode rows in two different ways. First, it reduces the latency of a refresh operation. This is because since refreshing a row is essentially restoring the charge level back to the cell and then perform pre-charge to close the row, the activation, restoration, and pre-charge latency reductions also apply to reduce the latency of refreshing a DRAM row. Second, since a single logical cell contains two physical DRAM cells, it has larger effective capacitance. Therefore, less refresh operation is needed for rows operating in high performance mode. We conclude that CLR-DRAM could reduce both the refresh latency and the refresh rates for rows operating in high performance mode. Now, let me quickly go through the evaluation part since the result is already covered in previous lectures. So we use a SPICE simulation to evaluate the latency impact of CLR-DRAM, and we show that CLR-DRAM can significantly reduce all four DRAM access latencies, which is TRES, TRCD, TRP, and TWR. We also evaluate the system level performance and DRAM energy impact of CLR-DRAM using Remulator and DRAM power. For the system configuration, we evaluate 5 configurations to simulate how CLR-DRAM would be used in future systems by different users in different situations. We configure X% of the DRAM rows to operate in high performance mode, and we evaluate 5 cases where X equals 25, 50, 75, 100, plus an extra case of X equals 0 to evaluate the configuration that all rows operate in max capacity mode. And we map X% of the most access pages of the workloads to the rows configured to operate in high performance mode. And our results shows that CLR-DRAM improves performance of both single core and multi-core workloads, and even in the case where all the rows are configured to operate in max capacity mode rows. This is because the added isolation transitions actually reduces the activation latency, and mainly due to the reduced execution time, we also save much DRAM energy. Our evaluation also shows that a row operating in high performance mode in CLR-DRAM can extend its refresh rate by at most 3x, and we show that such extension of refresh rate would introduce a significant DRAM a significant reduction in DRAM refresh energy, while only introducing a negligible negative impact on the performance improvement. We conservatively estimate CLR-DRAM to have a modest DRAM chip area overhead of 3.2%, and the DRAM capacity overhead of configuring DRAM rows to operate in high performance mode is like x over 2% when x% of the rows are configured to high performance mode rows. And we have more detailed discussions about overhead in our paper. We conclude that CLR-DRAM is a low-cost DRAM architecture. We also have a more detailed sensitivity analysis between the trade-off between reducing between extending the refresh rate and the increased activation and restoration latencies due to the reduced level of charge prior to the activation, and its system level impact in the paper. Our paper also includes some design details that make CLR-DRAM work efficiently. Now let me conclude my talk. So we propose CLR-DRAM, a capacity latency reconfigurable DRAM, a new DRAM architecture that enables dynamic fine-grained reconfigurability between high capacity and low latency operation. CLR-DRAM can dynamically reconfigure every single DRAM row to operate in either a max capacity mode where it achieves almost the same storage density as the baseline density optimized open plan architecture by letting each DRAM cell and its sense amplifier to operate separately, or a high performance mode where it has low access latency and low DRAM refresh overhead by coupling every 2 adjacent DRAM cells to operate as a single logical cell, and their 2 sense amplifiers to operate as a single logical sense amplifier that drives the single logical cell. Our evaluation shows that CLR-DRAM reduces all 4 major DRAM access timing parameters and improves average system performance and saves DRAM energy. We hope that future work can exploit CLR-DRAM to develop more flexible systems that can adapt to the diverse and changing DRAM capacity and latency demands of the workloads. Now, I will talk about some future works, challenges, and opportunities raised by CLR-DRAM. First of all, CLR-DRAM enables a new kind of heterogeneous memory system. Such a heterogeneous memory system offers two memory domains. One is a fast memory domain, and another is a normal memory domain. And unlike conventional heterogeneous memory systems like the HBM on Intel nice landing architectures introduced in previous lectures, the capacity of these two domains, they can be dynamically adjusted at a fine granularity. So this immediately exposes new challenges and opportunities in the research of more efficient management for such a heterogeneous memory system. So first, we might need new data placement policies to determine that like which virtual pages goes to which memory domain, and we might need like new management policies to determine and when to determine when and how that we migrate data between these two domains. And remember that due to the fine-grained dynamic configurability of CLR-DRAM, such a CLR-DRAM enabled heterogeneous memory system can actually have another choice other than migrating data as in the conventional heterogeneous memory systems, that is to actually change the operating mode of the row that the page is residing in. And in order to make use of this new functionality, we obviously need new management policies, and also we need to identify potential applications that could benefit from the heterogeneity in memory access latency and system memory utilization demands, and also from these applications and the system side, we might need new software designs and algorithms that are explicitly aware of the dynamically changing memory capacity demands, and thus the unused memory capacity can be used to improve performance. And we also need like semantically rich cross-layer system interfaces to communicate the information in the software and the applications to the system software, like the memory allocator, the virtual memory systems, or the alternative to virtual memory systems, so that the system software can make efficient use of these informations and map data intelligently and efficiently. Also, we might need new memory controller or even relevant parts in the CPU so that they can efficiently manage the bookkeeping of CLR-DRAM, which involves the mode switching of the row, handling the incontinuity in the physical memory space, and maybe even further, a complete reconsideration of how we do address interleaving in the memory controller. Yeah, and that is all of my talk today, and I will be happy to take any questions. Okay.
Okay. Thanks, Haocong. I think at this point we're running a bit late, so perhaps people can ask their questions over Piazza.
Okay. Okay. And actually, I don't see any chat.
Yeah, there's no. Yeah, I don't see any also.
Okay. Yeah. So thanks everyone for your attention, and if you're interested, I will be happy to answer any questions on Piazza.
Okay, that sounds good. Yeah, this is certainly a good direction in memory research. This sort of flexibility is much needed, especially flexibility that trades off different kinds of metrics is very useful, and how to take advantage of it, like outlined in the slide, is very important, of course. So there's a lot of interesting research to be done in this area for sure. Okay, let's take a break now for about 10 minutes, and then we will continue with the remaining two talks in the lecture.